We're starting our unit on polynomials and rational functions. And I'm assuming a decent chunk of today will be review. You've seen polynomials before. We're going to spend the next couple days talking about their properties, their graphs, how to find their zeros and solve polynomial equations, all that fun stuff. And then we'll move on to rational functions, which are related to ratios. What's a ratio? Something to something or something over something? Yeah, like a fraction. Rates of change fall in that category. Very good. Yeah. Specifically, the rational functions we'll be looking at are going to be a ratio or a fraction of polynomial to polynomial, which is why we're starting with polys. So, to talk about polynomials, we have to understand power functions. And we have a bunch of examples of power functions. Y equals 2x cubed. F of x equals x to the minus 2. G of x is 1/2 x to the 3/2. Yeah. What I'd like you to do is, based on that pattern that you see in the examples, I want you to see, if you're in your small group, you can come up with a couple more. So I'm going to give you about 60 seconds. I want everyone to come up with their own example of what a power function would look like. You have examples? Yeah? I want you to use the examples. Discuss with your neighbors what the pattern is. I'm going to pop some time on the timer. What's the pattern? Can you create another one? I'm going to use my random name caller to call on people, so everyone needs to talk about it. Did you make an e-hop pass? If you make an e-hop pass, I will let you go. Okay. Yes. Why are you throwing your neighbor under the bus like that? Choose better friends, Jordan. Choose better friends. You're welcome. All right, so let's see who's going to give us some examples. Where's my little random name generator here? Ooh. Marissa, can you give us an example of a power function? Is that what you said? Do we agree that that looks like a power function? I see some nodding and some thumbs up. Very good. Let's see, who else can give us an example of a power function? Julie, what'd you come up with? Four x to the third, does that look like a power function? Got some yes, very good. That is not what I wanted. Try that again. Go away. She's not here. Frowny face. Megan. She's going to pick on that back corner table today. What do you got? Do we agree? I see some nodding. Very good. Very good. So the question is, what is the pattern? You came up with some examples, so you must have found the pattern. What is the pattern? Yes, Bruno. All has the power of something. Good. So we know that it should have x to a power. Good. What else do we see floating around? Some of the examples have it, some of them don't. Fractions, there's a y equals or an f of x equals. and there is a constant in front. 2, 1/2, 4. Yeah. And sometimes we write it as y equals. Sometimes we write it as f of x equals. But the pattern is the same. Yeah. And the rules is the coefficient a and the exponent n are real numbers. And a, the number in front, is called the coefficient. We know n is called the exponent. A is a coefficient. What is the x called? The thing that is being raised to an exponent. What do we call that? Starts with a B. Base. Yeah. So our independent variable is the base, and it's being raised to a real number exponent and then multiplied by a real number coefficient. That's a power function. Notice that could be any real number n. So I could raise x to the 0 power. 0 is a real number. What's x to the 0? 1. Yeah, which is a number. So y equals a number, our constant function from our toolkit function, is a power function with x to the power of 0. Yeah, very good. We're going to go through some examples and vote which ones are power functions, which ones are not. If you think it's a power function, you're going to give me a thumbs up. If you think it's not a power function, you're going to give me a thumbs down. We're going to start with the first one. Y equals the quantity x minus 1 squared. Power function, not power function, but with your thumbs. I see thumbs down, thumbs up, shaky thumbs, thumbs up that went to thumbs down, thumbs sideways, thumbs up, both. It can't be both. It's one or the other. Pick one. What does this example y equals x minus 1 squared have that none of the other examples had? Parentheses and a minus. Yeah. So this guy is not a power function. Power functions should not have any addition or subtraction in them. Only multiplication and division, which is related to multiplication. Yeah. Good. Okay. Next one. Y equals square root of x. Y equals square root of x. Power function, not a power function. So I'm going to rewrite this and see if that changes your answer. Power function, not a power function. That's a power function. Yeah, this guy is. Yeah. Remember that radicals can be written as fractional exponents. I'm going to scoot sideways for a little bit. So we know that x under a square root is x to the 1/2. What about the cube root of x? What would that be? 1/3, following that pattern. Yeah, good. 4th root of x would be x to the 1/4. Why would my fan just die? I don't know. My fan just died. Funny face. Okay, I guess I'm going to be a sweaty mess today. That's fine. Ooh. We know what the outside does. The outside is something over 3. The exponent that's under the root becomes the numerator. It is 2 over 3. Yeah. And we'll see those again later as we start talking about more complex functions. Yeah? But all of those qualify as power functions because they can be written as x raised to a real number exponent. Okay, next one. Y equals 2 to the x power. Thumbs up, power function. Thumbs down, not. Does not depend. It is a yes or no question. Yes, it's a power function. No, it is not. Opinion. No judgment, just opinions. Mostly thumbs up, some thumbs sideways, and Megan looks like she's asleep. So, we're going to go back up. In our definition, what's in the base? The x. In this example, y equals 2 to the x power, what's in the base? 2. Not a power function. All power functions are going to be our variable x raised to a power. So x has to be in the base. Good. Next one. Voting with our thumbs. Y equals 1. Power function, not a power function.
What?
I just talked about that a minute ago. Now I know who was listening. X to the 0th power is 1. 1 times anything is 1. Yeah, so that is just an x to the 0 power. Yeah, so constants are always power functions. It means the exponent is 0, yes. Good. Last one. Y equals 1 over x squared. Power function, not a power function. Very good. I agree, because I can rewrite that as y equals x to the minus 2. That matches the pattern of a constant, 1 in this case, times x to an exponent. Yeah. Good. Perfect. If it's not written, what is it implied to be? 1. There is one of those. So all of these that don't have coefficients, their coefficient is 1. Yeah. So we want to understand power functions because we want to understand their end behavior. And I don't know what I was thinking when I put that blank there.
You don't remember what you put there?
No, I don't. If the function is a positive, if the... Oh. I got to think about it for a second. But I know that second one is if the exponent of a power function is a positive integer, meaning it's a nice, pretty countable number and not a fraction or a negative, we can use the exponent to determine the end behavior. Describes what the graph of a function does. Come on. You're going to see that end behavior written that way as x approaches plus or minus infinity, right? Approaches infinity from either direction. What is our function doing? F of x is doing what? That's our end behavior. The answer to that question is the end behavior. And if our exponent is a nice, pretty, positive integer, we can figure it out just by looking at the exponent and the coefficient on our power function. If it isn't, then we have to use other methods like graphing it. The upside is that polynomials use positive integer exponents, and that's the direction we're headed. So We have four cases. We can have an even powered exponent or an odd powered exponent, and we already know what those look like. If my graph, or if my function rather, has an even exponent, x squared, for example, what's the shape of the graph look like for x squared? A u, yeah, it's a parabola. We know it does this if its coefficient is positive, and it does this if its coefficient is negative, right? Happy face or frowny face. And that's true for any even powered power function. Anytime that exponent is even, if the coefficient's positive, both ends will do this. If the coefficient's negative, both ends will do this. For even powered power functions, the sign on the f of x should be the same in both directions, right side of the graph and left side of the graph. Even moves together, both up or both down. What about odd powered functions? We've seen a cubic function, y equals x cubed. That's an odd powered power function. What does our x cubed graph look like? Yeah, it looks like that S. Very good. So I know when it's odd power and positive, it looks like this. When it's odd power and the coefficient is negative, I flip that upside down. Odd power, the endpoints go in either opposite directions. Words are hard. Okay, let's practice. We're going to practice writing them using that notation. Yeah. Okay, the reason we're practicing this before we do our two examples is because polynomial functions follow the end behavior of the highest exponent in the polynomial. They're going to follow their matching power function of the highest exponent. We're going to see that in a minute. So we want to describe the end behavior of the power function f of x equals x to the 42nd power. I'm going to get two statements. I see interesting look on Alan's face. Do we not like the 42nd power? So as x approaches positive infinity and as x approaches negative infinity, I want to know what f of x is doing. And to figure that out, exponent, coefficient. So we're looking at, is the exponent even or odd? Is the coefficient positive or negative? So let's start with the exponent. Is the exponent even or odd? It's even. Ends at a 0, 2, 4, 6, or 8. Very good. So this is an even exponent, meaning I know that my ends do the same thing, both up or both down. Is the coefficient positive or negative? Positive, yeah. Meaning I know both endpoints go up. If both endpoints go up, what value are they approaching? Positive infinity, yeah, on both ends. Good. Yeah. Snaps. Perfect. Perfect, perfect. Okay. Same thing. Yeah, we do the same thing. F of x equals negative x to the 101st power. Jordan, is our exponent even or odd? Okay, y is odd. Very good. So we know the ends do opposite things. Alex, is our coefficient positive or negative? It is negative. Very good. So we know it's flipped upside down. If it were odd and positive, it would make my s. Now we're flipping it upside down. So it's this way. On the right half of the graph, as x approaches positive infinity, what does the function do? Negative infinity, yeah. Good. On the left half of the graph, as x approaches negative infinity, what does my graph do? Positive. Very good. So when we flip an odd function, it flips so that they're now going opposite. Very good. Snaps. Yay. All right, questions on power functions? No. Okay, then we're going to talk about a relative of the power function. We're going to talk about a polynomial. Polynomials are sums of power functions, specifically power functions that have positive integer exponents. So polynomials can be written as a coefficient times the variable to an exponent, and all the way down the line, yeah? Uh-huh. I know, we're in college math now, right? You've seen functions that look like that. You've been looking at them since like math 2. That's not anything new. We just haven't expressed it like that before. This is the general form. It describes any polynomial that could ever exist. And this particular form, where we're writing it, where the exponent is slowly getting smaller, n minus 1, n minus 2, all the way down to n is 0, which means it's x to the 0, is called the general form. That's the preferred form for polynomials. All of those a's is a coefficient. We know what coefficients are. And they can be any real number. Positive, negative. They can be 0. They can be decimals. They can be fractions. The only limitation is the coefficient that's in front should not be 0. Otherwise, that term isn't there and it's no longer a leading term. Each of those products, a times x to the n, is called a term. You will notice in polynomials, terms are separated by addition or subtraction. Anything that can be written in this form, even if it doesn't live in this form at the moment, qualifies as a polynomial. There is a catch in that you'll notice here, unlike with power functions, for polynomials, we are limiting in to positive integers. No square roots, no fractional exponents, no negative exponents, positive integers. Knowing that, I'm going to ask you some questions. Which of the polynomials shown below are, or which of the functions shown below are polynomials? Words are hard. So we'll start with our first one. Our first example says x of t equals 1.6 plus 5.2t plus 4.9t squared. Is that a polynomial? Marissa's nodding her head. Yes. How do you know, Marissa? The exponent goes down. Very good. 2, 1, 0. The exponents are positive integers. Good. So this is a polynomial with 3 terms. Yeah. Come on. Did Joby come back? Yes. Okay. Next one. H of x equals 5 times the square root of x plus 2. Brandy. Is example B a polynomial? Brandy says no. Who agrees with Brandy? I see some nodding. Alan, why do you agree with Brandy? How do you know it's not a polynomial?
Square root.
And we know that square roots are fractional exponents. This guy fails the requirement that our exponents must be positive integers. 1/2 is not an integer. That's a fraction or a decimal. Good. Very good. This guy is not. Next one. G of r equals negative r times r squared minus 4. G of r equals negative r times r squared minus 4. Diana is shaking her head no. Remember that it doesn't have to live in general form. Can you rewrite it so that it is in general form? And Alex and Ethan are shaking their head. Yes. If I distribute that negative r, I get this. Assuming I did that distribution correctly. Does that look more like a polynomial? Yeah. So this is a poly with 2 terms. Negative r to the 3rd and positive 4r. Very good. Last one. Last one. F of x equals 2x cubed times 3x plus 4. Jackie. It is? Is that a yes? Jackie says yes. Can I get a thumbs up if we agree with Jackie? I see some nodding and some thumbs up. Very good. I'm inclined to agree with Jackie. Because if I multiply that first term, I just get 6x to the 4th. And that matches that pattern. Positive exponents. Yeah. Nice, pretty coefficients. Yay. Very good. Perfect. So, most common, you're going to see these guys written so that the powers are in decreasing order. So that our polynomials in general form. And the reason we like to do that is when we look at the end behavior of a polynomial, it is the very first term, the guy with the biggest exponent, that determines what the edges of the graph look like. As x gets bigger and bigger and bigger, the guy with the biggest power is going to dominate over everything else. He wins the war. So in general, when we're looking at polynomials, we're looking at that leading term. The coefficient in the leading term is called the leading coefficient because mathematicians are creative with their naming. That leading coefficient is going to become important when we start looking at rational functions, ratios of polynomials. The exponent on the leading term is called the degree. The sign on the leading coefficient and the degree determine the polynomial's end behavior. Probably, but I wasn't sure. I'm pretty sure I finished typing this last night while I was sick, so don't judge me. The end behavior should match that of a power function that is equal to the polynomial's leading term. Meaning I can ignore the rest of the polynomial and just focus on y equals leading term. That power function tells me what the edges of the graph look like. So we're going to do some examples and then we'll be done for the day. All right, so we've got four examples here. We want to identify the leading term, degree, leading coefficient, and then describe its end behavior. That is a lot. I'm going to do one with you. I'm going to have you guys try some on your own. A says f of x equals 3 plus 2x squared minus 4x cubed. That is not in general form. So I need to search for the biggest exponent. And I see the biggest exponent is in its last term. So that is the leading term in general form. That's the guy I'm interested in. He has the biggest exponent. The biggest exponent is called the degree. Is the degree even or odd? Odd, yeah. Good. Is the leading coefficient positive or negative? Negative. Odd and negative. We know what odd and negative looks like. Odd and negative starts up high, comes down low. There's probably going to be some bumps, some hills and valleys in the center, but the edges starts up high, goes down low. Can somebody who remembers our notation tell me how to express that using math notation? Yeah, very good. On the positive side of the graph, the curve goes down. On the negative side of the graph, the curve goes up. Perfect. Okay, I'm going to put a couple minutes on the clock. I want you to try that same process with B, C, and D. And then I'm going to have some people either come up to the board or walk me through it. Yeah? Give you just a couple minutes.